Great. Well, DTS hacking.
Are we ready to go?
Yeah, let's rock.
I think so.
Who wants to go first?
Exactly. Yeah. Well, we can go first. We have this roadmap to share, which I promised you last week. DJ, do you want to post a link in the chat?
Yeah.
Thank you. So we have this roadmap that kind of gives somewhat of an overview of what we see as the things that need to be specified or implemented, for the scalable sharded consensus protocol stuff. Unfortunately, it doesn't show any of the work that we've already done. It only shows the work that we have yet to do, which means that's not a very good onboarding document. But assuming that we're comfortable with the sharding stuff that we've done so far, and I know Greg, you said last week that you wanted to go over some of that. I'm happy to answer questions about it. Then the sharding specification roadmap kind of makes sense. So let me know if you guys see it.
I can see it.
Cool. So basically, there's a bunch of parts.
I'm sorry, I can't see it. I got a 403. Okay.
Great. So the first thing that we kind of have in the roadmap is the whole validator strategies thing, which is very related to our conversation last week about expressing validators and messages and all of these things in PyCalculus.
Yeah.
And so we need to, move from our set theoretic something to language for specifying it, that it can include, behavior, specifically when they make messages, so that we can, have this validator strategies thing, but also how they make messages. Right now we have this estimator that kind of plays two roles, both the make message role and the validate message role. But realistically, you don't want to be computing the entire estimator every time. Instead, we have two different methods: one that makes a message and just picks something from the estimator, and one that validates a message, which will just check if the message is valid, which means checking if the consensus value is in the estimator of justification, without actually computing all of the estimator of justification, or without ever computing the whole estimator of the current protocol state that you're making a message from, because that's an infinite set and super unrealistic that you do that. And so, even so, the set theoretic specification uses, this estimator, which isn't really implementable even in the case of blockchain. And so, instead, we need to replace it with something where we make a block and validate block. And ideally, we show that, you can make anything in the estimator with a make message thing, and then anything in the estimator will validate. And I think, we have a very good idea of how to do this, because this is actually how we actually implement it in the prototypes. We don't actually implement the estimator. We implement, we have implemented the estimator for the simple prototypes, but with the sharding prototype, there was no way to do that. It's not very practical at all. And even the blockchain, the estimator that we implemented, we did a bunch of extra work that's kind of unnecessary in order to get all of the possible tips of the chain, but we didn't get all of the possible blocks that we could build on there. And if you don't have transactions, that doesn't really explode much in the blockchain, but in the sharded blockchain, it really does. And so we need to, at some point, we can't just compute the estimator directly, but we have to choose things from it and verify things are in it using some kind of, here we think of it as a function, but we're going to eventually think of it as a program, or something in some language that we can use to express all this. So the validator strategies idea is, we need to target our overhead latency node count trade-off and say when validators should make messages, and show that that's fault tolerant. So that's kind of the basic liveness thing that we need to do. And then the decision oracle for majority-driven properties is something that is still a work in progress and is kind of part of the core CBC Casper specification. And then another one that's kind of interesting is we need to do use a decision oracle to do state pruning, so that you don't keep all the messages forever and don't have this growing state. Instead, can forget messages based on the decisions that you notice. Which we've talked about for a long time, but is still not specified, at least not like fully. I think I guess now's not the time to do research on that. Okay, let's keep going. So so in the sharding, now we're moving kind of to the sharding world, whereas all that previous stuff was in just the full node CBC Casper protocols. Sorry, full node CBC Casper family spec. We need to actually do a light client spec for sharding to work out, because otherwise nodes will have to download like way too many messages from way too many validators, and the messages will be way too big. And so there's basically like two orthogonal angles of light client specification. One of them is using instead of sorry, 1 second. Yeah, so it's instead of receiving messages from all shards, you're only going to receive messages from some shards. So the idea is like when you look at the messages from validators, you may not actually look at all of the validators, even though in their justifications they include messages from all the validators, at least like once you do the closure. So the idea is like, okay, well, instead of actually having messages in the justification, we have like hashes of messages, and when we download messages, instead of trying to resolve all of the dependencies, we only resolve the dependencies from the valid set of validators that we care about. And like those are going to be the validators that have weight in the decisions that we're paying attention to. And like only those validators do we need to receive messages from, and that provides a good amount of like client friendliness, because like instead of downloading all the dependencies, you only download the ones from the validators that have weights and decisions you care about. And that is like the minimum really that you could do. And then there's the other orthogonal angle for the light client spec, which is the making blocks, making block headers out of blocks, and using like hashes and not sending anything to the client that they don't care about. So if they're interested only in some piece of the state, they only need to receive that piece of the state. They don't need to receive the whole state. And so instead of considering the consensus value to be the whole state, at least this is one interpretation, you consider it to be like the hashes or the summary of the state. And then the client asks about properties of those summaries, and they can answer those questions with the given proofs that include, the actual state that they're asking about. Like in Ethereum, we have this Merkle tree, and that would be like the state of the account and the Merkle proof that shows that collides with the Merkle root in the block header, for example. I'm not sure exactly what the plan is on our chain, on how to summarize or prove, or like to use a small amount of data to prove that your state is that this is like some state. But the idea is like, if you consider the consensus values to be like the whole state and you put all of that in the message, so the message is going to be quite large. And so instead, what we're going to do is put the minimum amount of stuff in the message that's required by clients to engage in a proof system that they can use to answer all the questions that they care about. I feel like I should stop for questions.
And I don't have a lot of questions. I have a lot of comments, but I was just waiting I was holding off until.
Well, I'm just looking for questions right now. Yeah. If anything I said was like not clear, that kind of thing. So there's two light client directions again. One of them is not receiving messages from all the validators, and the other is making smaller consensus values that we can ask about properties of using basically cryptographic assumptions. So basically, again, this is actually interesting, right? Is basically we're really going to rely on these cryptographic assumptions that these hashes work, in some way for the first time ever in the light client spec. And it's interesting just from the point of view of like the math involved. is very normal and mundane from the point of view of like normal cryptocurrency space, where everyone uses hashes all the time, takes them as given.
Do you think if you're doing this here, it also somehow makes sense to, bite the bullet and add public-private keys to the validators, like in the validator strategy stuff?
No, I don't want to. I mean, I wouldn't even call that biting the bullet. I would call that jumping straight to like a solution that's probably too primitive. Like I'm not even sure. I'm not sure myself actually. So I guess I don't know exactly what kind of signatures validators want to provide. I would prefer abstraction. So I would rather have an abstract system than a particular key pair system. But so I guess my answer is no. I don't see why
Cool.
you say that. Just because like you introduce one cryptography assumption, you might as well introduce another.
Yeah, essentially. But
And
fair enough.
I mean, I'm not sold. I'm not sold. Yeah, but eventually we are aware that like, we need source authentication so that like a Byzantine validator can't produce any number of faults just by themselves. Unless they are all the validators. Okay, so sharding estimator specification is this like next section that I'm hoping you'll scroll to. And basically we just have like, okay, we have the sharded estimator, and we want to verify it and understand like, okay, that is the right one, in the sense that like we have all the validity conditions, all the filter conditions, and that like we satisfy our atomicity guarantees. We feel pretty confident, but we don't proofs, you know what I mean? And I think we need proofs. Arbitrary shard rotation is basically we have a couple of these operations implemented, but not all three of them, if I understand correctly. So basically the sharding estimator with the shard rotation, which is basically like the balancing operations where the shards change positions, is still not complete, but so this is still some research required. And then like once the spec is done, we also need to kind of show or give some proof that is correct. Or ideally like have this whole correct by construction scheme. Shard creation destruction, where we create new shards and destroy shards. It's kind of interesting, and that's like, I would say I'm very confident in my spec, but also like, it needs to be written down and specified for other people, and needs to be reviewed. The routing system, it's implemented, not really specified anywhere too formally yet, but it's implemented and it looks really good, and it's super simple. And then the shard validator rotation is kind of interesting. It's like basically, how do we move validators around between shards? We basically use the messaging system and the exact same validator rotation protocol that we have in the Friendly Ghost, and it works fine apparently. But that's also something that should be checked out. This is kind of the way it works. Is like, imagine that validator is being sent by a message at this block. Then the next block will have a new validator set that excludes that validator. And if this block is receiving a validator, then this block's child will have this new validator in the validator set. It's super straightforward. The cool thing about it is that, when you receive the message, the validator set changes, and you don't necessarily know when that's going to be in some way. If you're, at least if you're the child shard, I mean, I guess there's not much. There's not that much control that you have. So it gives me optimism that we can force validators to rotate in a way that makes it really hard for an adversary to maintain control of a shard. So that's and so the arbitrary shard validator rotation is interesting and is going to be important for the load balancer. Then we have this like other subsection, which is like kind of more EVM specific stuff. You know, we need to make sure that we have account addresses that are unique across the shards. So that like when we, you know, so we have all of the shards either in all the accounts, either in all the shards or being sent from shard to shard. Which is actually the second point here. We're moving EVM accounts across shards. You know, because we want to do load balancing both by moving shards around and by moving accounts around to move accounts that talk to each other more closer together, that kind of thing. And then we have to provide like, you know, like a cross-shard communication model for like the EVM kind of, you know, understands like when you're making a call, like, and they're waiting for a return value, you know, like, that's totally fine if it's on this shard. But if it's on another shard, then like the EVM semantics like need to change, need to give, because like you can't wait forever, or if you do wait while like you're waiting on the callback, then like that does mean that the EVM has like paused in a state where like today wouldn't pause. And it's gonna have to like, you know, have transactions queue up in a way that doesn't have today, which maybe can be done outside the EVM. You know, actually I say here that it doesn't require you to change the EVM, but actually I figured out that it does. Okay. Anyways, so basically we have to make some changes to provide different cross-shard communication models. Then we have all the gas accounting and the charging for gas stuff, and the gas limiting and metering for the whole blocks. And then we have like the load balancer, which is going to try to minimize the overhead of the protocol and distribute the load at the same time. And that's like a big part of the spec that is, I think, you know, still, I mean, it's a part of the spec that's not done yet.
I have a question.
Sure.
So it seems like you're quite focused on like using the EVM here.
This whole section is EVM focused. Yes,
right. But in general, it seems like in the sharding protocol, you want to use the EVM.
No, I would say that I would say that outside of this part, so there's like a part that's like labeled EVM specific. Like outside of that, I don't see any EVM stuff up here. Right?
Yeah, no, fair enough. But if, I mean, this is like one kind of major part of the roadmap. It seems like, you know, in some first sharding version, you want to be using the EVM. And I'm wondering,
well, we already have this ETH sharding POC thing that I've been hacking at the ETH global hackathons, and that like I continue hacking on, you know, in a few days at the ETH Singapore. And so like, and like that is like basically like one of the reasons why. But the other thing is like, I mean, but anyway, sorry, I didn't mean to cut you off. Go on, sorry.
No, yeah. That was, I mean, you were answering my question, I guess, already. So I guess the question is like, wouldn't it be better if we were able to kind of define like a more abstract model, like insist on unique addresses across shards is something we can say about like whatever kind of VM we end up.
No, because you don't know that you're gonna have account addresses in your VM.
Right. But so this is what I'm saying. Like we could insist like you need a VM with account addresses that are unique.
Oh yeah, shards. I see. So we could just like instead of say the EVM, we could just like you like mention the properties of the EVM that we're using.
Yeah, exactly.
But it doesn't have to be a VM, right? It could be some execution mechanism, right?
Yeah, totally.
It could be an interpreter.
Yeah.
It could be all kinds of things.
100%. And actually, I think like if you're talking about like, oh, what we really want is actually somewhat far removed from this, because like we're talking about blockchains on every shard. Like a blockchain is like not super concurrent and not super application specific. Like we would much prefer something like you give us a term in some programming language, and that programming language is semantics, and then we like generate a sharded blockchain consensus protocol that is like or sharded consensus protocol, like not blockchain, it's like a sharded consensus protocol, like specific for that term, you know, like that's like the ideal.
Some rewrite system.
Yeah, or it's some rewrite system, exactly. Yeah,
that covers VMs, that covers interpreters, that covers
exactly a
wide range of things.
Yeah. So ideally, you give me some rewrite system or a program, and I'll fetch the programming language semantics and make a rewrite system out of it. And then make a consensus protocol that's like sharded, based on the concurrency that's available in that, like semantics or whatever. But this is like, you know, I think, more difficult for me to pull off than the blockchain thing right now. And so there is like some extent to which this is driven by some idea that like we don't want to spend 10 years chasing after the Holy Grail, although we do also, but also have to deliver things a little sooner so that people are happy.
So I guess one of my comments could be phrased as a question. How do you decide, or how do you characterize decisions that a particular shard is interested in?
So in the so in like the blockchain thing, basically the question is like when you're asking if a block is in a shard, that block is going to have a shard ID in it, and then only the validators that are on that shard will influence whether that block is in the chain on that shard. And the validators on its parent shard and the validators on its parent shard. But basically, you don't need to look at all the messages from all the validator sets from all time.
Yeah, no, I understand. I just wanted you to be crisp about the characterization.
Okay.
Yeah.
Was that sufficient? Was that good?
Yeah, I mean the way we've done it in our more abstract characterization is you've got even though both of those lattices are complete in some sense, you're not interested in all possible subsets of names. You only have some sparse tree that lives inside that lattice, or sparse graph that lives inside that lattice. And similarly, you potentially only have a sparse graph of the set of all the power set of the validators, right? And then you have an assignment between those two graphs.
Yeah, that makes sense. Yeah, so we have I think a much more specific instance of something like this.
Right, and then
based on what block you care about, you have to you go to its pre-block to figure out what validator set determines whether it's in the chain, given that its pre-block is in the chain.
Right, and then and then you can potentially create a new validator set if you need it in order to address something.
Yeah, I think a validator could, not a client, but a validator could,
or a group of validators could. Yeah.
Right.
Yeah. Good.
I mean, if you want to do everything with the optimistic execution so that you get the lowest overhead possible, a single validator could.
Yeah.
But it makes it the worst case overhead worse.
Yeah, well, I mean, it's also a bit tricky from a security standpoint, right? My biggest concern is that you get these low validator count fringe, and then those can be picked off by attackers, right?
Yeah, and I mean, even the idea of a small weight attacker doing damage because everyone's being super optimistic is very real.
Yeah, exactly. Yeah,
and so I think, but I also feel very much that it should be we should create a marketplace where it's possible for people to provide the best service, even though the best service may be, a thing where you're passing really efficiently, although with not much redundancy, or with not much redundancy, because every system is super fault tolerant, but in a way where failure might cause more delays.
Yeah, I understand.
Yeah, but it's but for now, I'm happy to just have it be unrestricted. Kind of at this stage of the specification.
I understand your methodology. Yeah. Yeah, you don't want to optimize prematurely.
No, definitely not. Yeah. So let's keep going here. We talked about the cross-shard communication model. I'm not sure if we talked about it enough. We are interested in this problem ultimately of avoiding deadlocks if we're going to do synchronous cross-shard communication. I don't know, we've talked about that at great length over the years. I still don't feel like I could give a type system for the EVM that will detect deadlocks. Or even, I don't even know also how to keep track of the deadlocks as it's happening. But I'm sure that, you know.
It's not possible to deadlock in the EVM, right? You have run to completion.
I think that with synchronous cross-shard calls, it'll be a different story.
Oh, yeah.
Which we do because contracts can call each other, like mutually.
Yeah, I understand.
Another question that came up during this discussion is like, oh, do we want to guarantee? So right now we have like a message is being received by time to live, but we don't have any guarantee on the amount of blocks that we need to wait for a message back. We could potentially restrict the fork choice rule and possibly the block validity rules in order to, I think also the block validity rules in order to guarantee timely return messages. It's an interesting one, and I mean, I think it would be nice, and I don't think so bad, but it's one of those things where, okay, we're basically like adding restrictions to the fork choice rule and the validity conditions to make it harder for validators to do something that we don't want, which they might not do anyways, but isn't fatal, like in the same way that some of the other validity conditions are, right? Like the other validity conditions, like if you come back just fine if the validator is like, you know, are doing a good job. And if they're not doing a good job, then the restricted protocol is really just gonna, you know, it's, I guess, like if they're being malicious, then it might help. But if they're incompetent, I think that it might just create liveness problems as they have to orphan lots of blocks as they fail to synchronize. So it's, you know, and also not to mention the additional overhead of the validity conditions, which is something I normally don't think about too much, but which I know other people are very concerned about. So also I actually mentioned the load balancer and the gas metering and stuff. And we have like the other distributed systems, like the validation protocol, the availability protocol, the gossip, the like interface for clients. The engineering and efficiency improvements. I don't know if they're in the right section right now, but basically we have like some optimizations that we know that we can do or should have. And also, you know, hope to take advice on and have like engineers work on making these things go really fast. Great. So yeah, please.
This thing that says Web3 interface, do you mean client interface, or do you mean like you actually want Web3?
No, I mean, clients use Web3 today, right?
Yeah, but you know.
So we're gonna like extend Web3 a little bit.
Oh no. Okay. I might say, like, you know, redesign probably. No.
Like you want to, you think it's necessary, or you want it?
So like this is just something that's come out of my conversation with like client developers who like, you know, for example, you talk to Peter about Web3, he'll essentially tell you it's like completely lunatic, and it just kind of came into existence because like, oh, you know, these things might have been nice, but it's like doesn't actually really make a ton of sense.
Well, you know, I mean, I think there's a lot of people who have that complaint, but they usually, I think, are complaining about the like the fact that it doesn't do async, not about the actual.
No, this is about the actual interface design that the complaints about. So.
Okay, so I usually hear people complain about the synchrony, like the synchronization model, with the way that like it's just like not compliant with like normal JavaScript stuff.
Yeah, I mean, yeah, that's also.
Although I think to me that seemed like it could be solvable. Yeah.
Yeah, totally. Yeah. So, but I think in general, like, I don't know. I mean, here's what I'll say. Like, it seems like within the Ethereum 1.0 community as of now, there's a big push to like change a lot of this stuff. And like,
okay, well, I'm just trying to give people what they want. You know, I mean, I'm happy to do something else.
Yeah, well, and anyways, I guess
If
it's
that's what they want,
sure, I hear you. I guess it seems like the most important thing isn't necessarily to give people what they want. If they expect,
well, no,
if it's like terrible, it might not make sense.
well, they might. I hear you, but also, the less disruptive we are to the existing. The hope. So here's the hope. I guess the hope is that like it'll be easier to get other people to like take responsibility on these things if if it's like already a project that they're already working on. So that, and like and also there's like, and it's also somehow easier if we change less stuff. So like I thought it might be like taking advantage of like a kind of network effect of people who are interested in using Web3. But if like the devs are building something else and they would rather see something else, I'm not going to say no. If anything, we should. I feel like I'm done here, and I have taken enough time. But I'm happy to field comments and questions.
Well, in general, I'm heartened to see the desire to start using behavior as a part of the spec. I think it's long overdue.
But also like we're in some way we're still making progress just on the data types.
I understand.
Like if the data type progress had stopped, I would wholeheartedly agree with you. But like we still make loads of progress just on data types.
Yeah. I get it. Program and data are not actually distinct. It's a holy grail to try to find a good dividing line between program and data.
Okay, well, I guess what I mean is like
I'm just teasing you. I'm just trolling you, dude.
I guess I mean set theory. No, you got me.
You
got me.
But to that end, I realized that part of what might have been confusing last time we spoke is that I was just using the program structure to retain the data content, but the time and causality was reversed in the encoding I gave last time. So I wrote down another encoding, which gets the time and causality correct, as well as
same document.
No, I didn't put it in the document. I wrote it again. Okay. It's another one-liner. So what you do is you use a join across all of the validators' IDs in the history of them. And once you've gotten values from all of those, then you release the value that's associated with M on T, where T is the target that has received the message. And in parallel, you do the recursive call across the history. So this will build up a bunch of for comprehensions and outputs, right, all the way up to the top, where if you plug in the initial conditions, the initial validator guesses, that will then cascade throughout the four comprehensions. So the next there'll be a level of four comprehensions that's waiting for those values, and they'll pick those up and then and then release some more messages, which will then be picked up by more full comprehensions and so on. And so you'll get.
Do you quote all this to keep it as justification, or
you don't need to? You can do that too. That's an extra level of sophistication, but it's not necessary. The only thing you have to be a little bit cautious about is, in order to get the causal structure exactly right, you have to. Like, you can't have a later thing stealing data from an earlier thing. So you have to kind of, mess with the namespaces a little bit.
I see. You have to do some hiding.
Yeah. You have to mess with the namespaces a little bit. Yeah, that's
okay.
But in general, it's still a one-liner specification.
So
So
here's a question that I had, Greg. I'm not sure this is how reasonable this is, but like, how would you feel about if I just like use set theory with the pi calculus and like set sets around and use just like set builder and like normal kind of set theory stuff, um, unions and stuff, and just like added some terms to so that things are being sent around and have like positions.
so 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 the general impulse is a perfectly reasonable one, right? We can certainly talk about sets of processes, right? But now
I want my processes to have sets, and I want them to be able to use all of the math stuff that I normally have to use and talk about. Not necessarily actually, but just like in the spec.
yeah. So
Or like
so but this is what I was trying to get at last time we spoke. So the in general, if you look at your notation at the beginning of your spec, what you're really assuming is a kind of functional programming language with an embedded, sets data type. And that's a perfectly reasonable approach, except for the fact that you're in a concurrency setting. So you could also imagine, and we have implemented an extension of the row calculus that has, sets as a basic data type, right? So that's a little bit a little bit closer to what you need.
Yeah, that's cool.
But it's also relatively heavy-handed. And so I want to like if you want to be parsimonious, I just want to observe that in the same. So if you think about functional languages, and this
No, I
goes
mean, I
all
understand. You can implement everything, like, you could re-implement like the entire foundation of mathematics in like from like
so
in the
sort of
pipe.
sort of kind of, but let's get more pragmatic, okay? So if you think about functional languages, and this is it's easier to see in Lisp than it is to see in OCaml, but it's still true in the typed languages. So in Lisp, S expressions, which are effectively lists, go hand in hand with the programming language. It's like it's the best fitting data structure for Lisp, right? And there's good reason for that, because the syntax of Lisp is essentially an S expression. So list and functional go together. So list is effectively, right. It's the difference between list and set is
a functional data type. You'd call a list. Would you go that far?
There's some subtleties there that I want to avoid, because I don't want to spend a lot of time
Okay.
disambiguating those subtleties. Okay. So but what you can say is that between sets and lists, there are two equations, right? And one equation is that it's commutative, right? So with sets, union and intersection are commutative, whereas append in lists is not commutative, clearly. And the other thing is that sets are idempotent, right? Meaning that if I take the union of a set with itself, I get back the same set. Whereas if I append a list with itself, I don't get back the same list, right? Because lists keep copies of they keep information about the number of copies. So list is really the data type for functional languages, and you can always build sets on top by forgetting ordering and forgetting multiplicity count, right? And so there's a sort of having that in the back of your mind when you think about extending your language with data types is a useful trick, right? It helps you know what is good fit and what's a little bit more work. And now if you move over into the row calculus setting, I'm just going to talk about row as opposed to pi, because pi has a lot more moving parts. Okay. So in the case of row, there's a corresponding best fit data type, and that's the multi-set. So a multi-set is halfway between sets and lists. So it does allow for duplication, right? So multiplicity is kept around, but commutativity is added, right?
So,
And
so let me see if I understand. It's like a set where you keep track of how many of each, how many times each element showed up.
that's exactly right. But you can't tell
Okay.
order.
So it's
Right.
not like a string. It's like the binomial distribution to the string of bits.
Yeah, that's one way of thinking about it. So, the trick here is that's worth understanding is that derives directly from the par that's already a piece of the program structure, right? So par is effectively multi-set because it's commutative, right? P par Q is Q par P, but P par P is not the same as P, right? So that basic
Oh, cool.
program, yeah, that basic program structure is where we're encoding the collection structure. And then once you understand that, then understanding how you encode JSON in row is just totally straightforward, right? So like where the JSON field value thing is just doing an
Okay.
output at
So
the
you,
field.
so you don't need to quote them because they're already data.
Yeah, right, exactly. So now once you kind of grok that, then it becomes, then you could certainly, if it's convenient, you can avail yourself of all set theory and all of that and just assume it as, you've got row terms and set theory and just do it that way if it's convenient. But if you wish to be a little bit more parsimonious, and the reason I'm suggesting parsimony here is because the more parsimonious you are, the closer you are to something that you can implement directly. The more extra math apparatus you have, the more when you map that onto programs, you're going to have to carry all that apparatus if you're going to carry the proofs over. Or you're going to have to translate your proofs to something that has slightly different structure.
Well, you end up writing new proofs that like this thing implements something like
Yeah,
in there.
so right, and so
Like so for us it's like we implement set membership instead of like calculating the whole set, for example.
for example, that's one way of thinking about it, but it gets trickier and trickier because set theory is really far away from programming. It really is, because sets are wild and crazy, and they're a lot crazier than we think they are.
They're a lot crazier than multi-sets.
Yes, they are.
Wow, okay. That's interesting. I guess it's because of the linearity. Like, is that why?
Well, basically, lists are much closer to what you find in computers.
Okay.
Right. Just think about it. Arrays are what you find in computers, right? That and lists are just sort of generalized arrays, mildly, weakly generalized arrays, right? Because arrays are fixed size and lists are.
Yeah, that's what I thought. Yeah.
Yeah. So anyway, so the point I'm trying to make is parsimony allows you to get to this ideal, or allows you to take a few steps closer to this ideal where the proof is the program. So if you keep thinking Curry Howard in the back of your mind, that at the end of the day, your proof should be your program. In other words, the program is the witness or the hypothesis that or the theorem that you're trying to state, right? And if you keep sort of, it doesn't have to be a rigid methodology, but if it's sort of a gentle guidance, then at the end of the day, when you're done, every proof basically comes down to a term that evinces the property you're trying to establish. And then it like that may not always be efficient, but it's not a bad starting place. And then you can do correct by construction transformation techniques from the term that you've got as a proof to a term that could actually run efficiently. And that's the general methodology that I've been
So when you say that you have the term as the proof, do you mean that you have like, a proof on the types of the term?
So how do I say this? They're formulae. You're trying to say something like,
Mhm.
for all states, if we make
Yeah.
under these assumptions for all states, we eventually get to this other state, right? And that state has another property which it's safe, right? So that's a formula, right? And then the term essentially encodes the transformation of any given state. So it's like a function in one sense, but it's like a process in another sense. Because when you say something like "for all there exists," what you're really doing is you're saying, if you hand me one of these, here's a recipe for turning it into one of those, right? And that function or that calculation or computation is your term. And that's your proof, right? The proof is really the steps that you go through in order to, well, if I'm in this state, then I do this, or if I'm in this state, I do this, etc. And that recipe, right, gets encoded as a term in whatever language, whether it's functional plus set theory, or row calc plus set theory, or row calc plus monthly sets, or whatever it is,
Mhm.
right? And then the term it can be the beginning of your implementation.
Right.
And
No, I mean, I get
and
it. I think the idea is pretty clear that the spec. Uh, so so but this so yeah so this so the idea is just I try to identify as much as possible of the spec in the program.
right to the point where if you're lucky, your spec becomes the architecture for your running thing, and that's really, then at that point, you've taken to heart correct by construction.
Mhm. Yeah, to the software, not just to the spec.
Not just to the spec. That's exactly right. So the software is literally correct by construction, because every program in the software, well, as a starting point, maybe it's not efficient, but every piece of code is literally an element in the proof of the properties that you're trying to establish for your system. And then to get to an efficient one, you go through program transformations where you're preserving equivalence.
You say element of proof. I mean,
Well, because you're just
isn't it more like it's like inhabitant of proof? It's usually not a proof. Isn't normally considered a set, right?
What I mean is that the proofs usually are like you have a theorem, but before you have the theorem, you might have a few lemmas and a few corollaries, right? And you stitch the lemmas and corollaries together in a particular way, and then you have your proof. Yeah.
Mm-hmm.
Right.
Sure.
And the proof of your theorem. So for a particular lemma, you're going to have a particular term, and for another lemma, you're going to have another term. And then when you stitch the lemmas together, that's equivalent to stitching the terms together. And that larger term should be the term that is the proof of your theorem.
You mean which has types which satisfies the type, which is your. How is it that?
Again, so
Sorry,
no, it's okay. It's totally cool. I mean, it takes a while to think like this. So the theorem is some formula, and I'm trying to use examples to make it more concrete, like for all states of this shape under these assumptions, we can get to this other shape state that is safe.
I think we can agree that this theorem is a formula as a type.
Great, good. Then in order to give a convincing proof of that kind, I need to check the time. Sorry. Okay,
You
yeah,
have 7 minutes.
I got 7 minutes. Okay. In order to give a genuinely satisfying and convincing proof of a theorem like that, what a computer scientist and would want, perhaps more than a mathematician, is, well, show me the steps. If I give you a state like this, how do I get one of those, right? And the steps, or the transformation process, that's a term. That's a term in some programming language, right? And
Sorry,
that's
the program takes those steps, or
the program.
the steps are the program.
The program takes as in, and then it goes through some calculations on that state, and then ultimately produces, the resulting state. So this is why, it's very tempting for people to think of these things as functions.
Wait a second. These states now are assumptions and conclusions, or
No. Remember, our theorem was of the form, for all states. Like, and I'm trying to use states because that's what Casper uses as its basic, calculational universe of discourse, right? So Casper is formulated across some universe of states, right? And safety, as an example, is going to be of the form, for all states that satisfy these conditions, we can get to states that satisfy these other conditions. That's a generic shape of safety. I'm couching it in this particular way so that we can think of it as like a function, right? And so the term that is the proof is expecting the client of this term to produce a state that satisfies certain conditions, and then it's going to inspect the state on the basis of the structure that must be present because of this notion of the conditions that are there, and then it's going to go through a massaging of that state to get to another state that satisfies these other conditions. That's the and any sort of argumentation that doesn't do this, and like, here's an extreme example, argument by absurdum, right? So you say, well, let's assume that the state, doesn't have these properties, and then we show that we get to an absurd condition, right? Something that doesn't sort of actually produce the resulting state would be very, very dissatisfying to a computer scientist, right? So you really, really want that the proof itself is going to go through a sequence of transformations that will actually produce the state that you are interested in.
Well, so I mean, so I'm trying to make sense of this via Curry Howard, where I'm trying to think of these steps as the actual steps in the proof.
Information, or constructing a new state based upon that information.
Okay, well, wait a second, Greg. You only have 3 minutes, and there might be other updates.
Oh, sorry. Yeah, go ahead.
I'm not sure if we should continue going to the deep end. Does anyone have anything that they have to key us in on? Or want to? I guess
it was just a private conversation. I'm sorry.
No, there's other people here too.
No, so anyway, I mean, it's really, if you do the just look at your own proofs and see if you can identify the recipes, so that the proof is really the way it's going to look is, go ahead and give me, I'm assuming you've given me, the characterization of the dependencies of the proof, right?
Mm-hmm.
Right, and then you're gonna inspect some of the information in those representatives of the dependencies. You're gonna make some calculations, and then you're gonna produce, the result, or I mean, and of course, there's going to be some
Well,
branch.
the theorem, right? There's like the last line is like the theorem.
Well, the last line, yeah, but the last line is going to be a witness for the theorem.
Well, no,
Right.
it's the statement, it's the formula that we're trying to prove.
Yes, but
yeah,
yeah,
Jesus.
It's the
I'm not sure.
witness for the formula. Yeah, exactly. So either you're going to produce a new state, or you're going.
Okay. So basically, rather than saying, for example, if the fall count union of two states are less than t, then we have
Yeah.
then we'll say if the union of these states is less
Yes.
than
Yes.
t, and then but somehow it's only, you have to guarantee that like
Now you've got it. Now you've got it. And so I'm excited. I think we're moving in this in a good direction. I gotta jump to this other thing.
It's been awesome. Thanks for the stand up.
Yeah, thank you. Ciao.
Bye.